Hi everyone, are you able to hear me and see the screen clearly? All right, so shall we start? All right, so great. Let's get started and let me give Robin the permission to record. Okay, hi Bintao, hi Praveen, hi Robin and Shivam and Tanmay. Great to have all of you in the session. Are you able to hear me clearly and see the screen clearly? All right, great. So yesterday we talked briefly about XGBoost, and it's called extreme gradient boosting. Okay, extreme gradient boosting because in this it does a lot of optimizations for while boosting the performance of the trees. Okay, so it's kind of a really good good algorithm, and the derivation or the maths underhood might sound daunting at the first. Okay, but I would love to give you a quick overview of XGBoost, and I suggest that you go through the paper as well as go through the code at least once to get a picture of what's going on underneath. Though you don't need to understand any of the maths or any of the derivation before using XGBoost. Okay, so boosting is essentially boosting is essentially boosting is essentially chaining the various you can say the classifiers or regressors, or we call them estimators as a general word. So chaining various estimators in order to improve the previous one's performance, right? And this particular XGBoost, the derivation of XGBoost is little daunting because it requires a mathematical foundation. But I would love to give you an overview. If you have more questions, I would love to answer. As well as I would recommend to you to go through the paper as well as through the presentation of Tianki Chen. Tianki Chen's presentation, I'll just walk you through, not because I want you to learn every part of it, but because it serves as a great introduction. And since we have already gone through most of the machine learning, this makes a lot of sense to us. Okay, so the reason I want to walk you through Tianki Chan's presentation is because it gives a very good overview of machine learning, what we have learned so far. So it will be kind of a revision for us as well. All right, AVS, Binta, Pavan, Praveen, Robin, Shivam, and Tanmay. So, so I would love to give you a quick overview, and thanks to Tianki, he basically went through the entire machine learning very quickly in this tiny presentation. Okay, so So these are the standard notations when we talk about machine learning. This is XI is the training example, and how to make predictions. If it's a linear model, then yi, the hat one, represents the prediction, and it's a sigma of summation of weight as well as weight, and multiplied by the individual value. Okay. A question from Bintao is, could you teach us A/B test? Okay. So A/B test is not much of a machine learning. It's more of uh, more of a software engineering, and there are many frameworks available for A/B testing uh, in case of your web application. So mostly A/B test is used with there, but yes, A/B test could be used in case of doing the say analytics. And let me see if I could come up with something there. Okay. All right. So should I go ahead with this discussion with respect to the. All right. So I hope everybody is clear about these notations, right? In the linear model, all we do is multiply, we come up with these weights and multiply each of the individual element and then sum it up, and that's our prediction. And then we basically subtract this prediction our from our expected one, and then observe how much is the loss and so on. Okay, so if it's a linear model, this is what's going to be. Okay. There is no link as such for this one. Okay. I would give you the URL. You could download from there. Okay. And since yesterday it wasn't working, right? So in that case, you should go to if let's say there's a website that's not working, you can generally go to the web archive and then get the particular version from there. Okay. So yeah, I just kept it in just in case the website goes down, like the way it did yesterday. And yes, in this one, okay, there was a link to the paper getting started with, okay, these slides. Okay, you should take a look at this. All right, these are the general public slides. Great. All right, so great. Let's get started. And right? So in linear model, all we do is we come up with weights such that when we multiply with the individual the feature values, then we get the predictions. And the predictions, we can have different interpretations. When we have like normal regression, then the yi is the normal the prediction score. And if we are using the logistic regression, we generally convert it into basically something like 0 and 1, and in that case we apply that logistic function for predicting a particular class and so on, right? So the things we need to learn from data is essentially the model. Okay, in case of linear model, then we have theta with all these weights, right? The other part that we learned earlier was that the objective function theta is having two parts to it. One is called the loss, the actual loss, right? Like mean square error or something like that. And the sigma, which is regularization. Like we learned earlier when we were studying the training models. At that point of time, the sigma was there were different kind of values for sigma, and that's basically the general way of looking at uh, the objective function. So this is for regularization. Basically, it measures the complexity of model, and overall objective is to minimize the training loss as well as the complexity. Okay, training loss as well as the complexity both needs to be minimized, right? The loss could be squared loss. It could be the logistic loss, as we see earlier that when we are basically measuring how well is our prediction, we came up with this formula, right? So that if the predicted class is same as uh, the the actual class, then the loss looks like this, right? If it is same, then the loss will be 0. If it is different, loss will be very high, right? So then the regularization term could be in case of the regression, it could be lambda multiplied by weight square or lambda multiplied by the mod of weights. And there is basically lasso, and I think this is called ridge. And then there is what was the third name? Lasso, ridge, and there was one more term we learned where there was both of the terms together, right? Okay, so that was lasso, rage, and there was one third one in which there were both terms. Okay, so I hope everybody is clear so far, and right. So the conceptual separation between model parameter gives you the engineering benefits, right? Think of how you can implement SGD for both ridge regression as well as logistic regression. Okay. Now again, so why do you want to contain two components in the objective, right? So optimizing training loss encourages predictive models, and optimizing regularization encourages the simple models. All right, that's what we learned earlier. Now coming back to a regression tree. A regression tree is nothing but like a big decision rule, same as the decision tree, contains one score at each leaf. There is in this there could be at each leaf there could be many instances, and the whole leaf has a single value as a prediction. Okay, and each leaf has a single value. So when we are saying age is greater than 16, all of the instances whichever come to the no side, right? They will always have the same value. Okay, and this information will use it during derivation. So we have the various input points, and let's say we are doing the classification from our tree. So let's say we are trying to answer the question like, does the person like computer game? So we have prepared this based on the data, and we can see that if age is less than 15, yes. Is it male? Yes. Is it no? If it's not male, then this. And similarly, if age is greater than 15, then this part, right? So here +2 means yes, the person like computer game. Person like computer game little bit, and this one is very low. Okay, right? So so there could be, as we learned in earlier, that we could have an ensemble. An ensemble contains multiple trees, and since these decisions, since these what do you say, these conditions are formed based on the various features that are available to us. And if the data is reordered or the sample is different from one tree to another, there could be another tree that could coexist at the same time. If we are creating many trees, the first one was on, let's say, 90% subset, and second one was on another 90% subset. So the trees could have different structure, right? So like the first tree was this, the probability of a given person was 2.9, and the second tree basically used another feature called use computer daily, yes or no. Imagine that we have three columns. One is age, other is like gender, and third one is the use of computer, whether daily or not. Okay, so here when we ask the same question to another tree, there'll be a different answer. Let's say this one, we go here and ask if this what will be the probability of playing the computer games. So this one, let's say, said zero point 0.9, and this one said 2.9. We can basically, the prediction is overall sum of this as well as this, correct? So essentially the prediction is going to be the sum of the leaves, sum of the predicted value on the leaves. Okay, is that right? So far everybody is okay? So we will feed the same, let's say we want to do prediction for him, for this person, we feed it in first tree, we get some results, we feed it in second one, and so on, right? So what will be the prediction for an old man who hardly uses a computer? From the tree one, it'll be -1, and from this side it'll be zero point 0.9, so it'll be -1 minus zero point 0.9, so it'll be minus 1.9. The chance of this person playing computer games is very low. For a boy, as per this particular tree, the chance is +2, while in this one it's zero point 0.9, so it's 2.9, right? So you can see that the this is how you can see that this is how we have a tree ensemble. If we have like 100 different trees, if we have 100 different trees, then the predictions become more and more stronger and better, right? And all these trees generally should be diverse, right? Some would be dividing based on age 15, some would be dividing age 20, some would be dividing based on first gender, then the age, then some will be dividing based on some other feature, and so on. So that's what is an ensemble. In an ensemble, right? In an ensemble, we basically have many trees many trees and so on. Okay, so in the case of extreme gradient boosting, what we do is we keep on adding the trees, and we add a tree which improves our objective function. Okay, we instead of thinking about just the way we do always, that we put like a model and then we see whether our loss function is going down or up. Accordingly we tweak the weights. Here we are going to tweak the trees. Okay, here we are going to tweak the trees and so on. Okay, just like in usual linear regression, we tweak the weights. Here we are going to tweak the trees. All right, is everyone with me so far? Only Praveen. Okay, a question from Ajay is that okay, good question. Yes, it is a little harder point, and I think others would also be having the same feeling, right? That if we are combining weaker and stronger algorithm, then how can weak and a strong algo combine to make stronger than right than the strongest, right? Will you be able to talk it through once more? Okay, okay. Does anybody else has the same question? I'm sure others would be having same question. All right, all right. So, right, right. Okay, okay. So Praveen saying the people's recommendation is one example, right? And yeah, people's recommendation as in when we are in that KBC, in India, there is one TV show, and in the US there is another. I forgot the name. Can somebody remind me? It's a popular quiz show, and right. So one term that confuses us in this is the weaker algo part, right? So weaker algo in general means better than the random, meaning something that gives us more than 50% probability, correct? Yeah. Who wants to be a millionaire? Thank you, Tanmay. So in those TV shows, what they do is they basically ask sometimes there is a lifeline in which you could ask the question uh, to the audience or to the general public. And there, if there generally the popular vote gets right? Gets right. The reason is that if, let's say, the individual, so individual is random, right? Individual is better than random. Okay. So if it is random, that means chances of yes or no is equal, correct? But if let's say, but if let's say there are 1,000 people, right? And you ask them a question that is is war good? All right. On an average, let's say everybody has a feeling that tiny bit. So let's say on an individual, so out of 1,000 people, an individual on an average says 51 times that no, war is not good. Correct. So if there are 1,000 such individual, the majority would be the chance of majority would be very high. Okay, so here when we talk about ensemble, it's basically we're looking at the majority vote. Okay, the majority vote. So to get the majority vote is something that changes everything. Like in case of a political scenario, let's say there is a country in which there is people voting for somebody, right? And there are two leaders, and people have to choose between the two, right? So they just have to make the people slightly bit biased towards them. If people are slightly bit biased towards one of them more than the other, just slightly bit, they will they will basically win the election. Okay, that's exactly what it means by the weaker algo, that they are slightly bit more biased. Okay, or you can say slightly bit more giving the prediction towards something, not absolutely random. Okay, so what else can I take the example? The coin example was that if we throw the coin, which is a bit biased, more than 50%, right? So what happens is that the 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 predictions of one are aided by predictions of another, and since we are just since we are basically summing up the probability, we are counting the majority. Therefore, their values add up. Okay, the values add up, and the 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 weaker algorithms could make up for a very good prediction engine. How else can I, right? Okay, okay. So, does it make sense? Or if the coin was not biased, the theory was not hold correct. Let's say let's say the coin was absolutely like 50%, not even not 51%, 50% head, 50% tail. No matter how many times you throw it, no matter how many times you throw it, the majority and minority will always be equal. Okay, as in head and tail will be equal. There will be no majority or minority. Okay, so the thought experiment of the coin is one great example, whereby what was happening is, as we were throwing the coin, the probability was adding up, right? So we threw the coin first time, we got a head, then we threw another second time, we got the chance of getting head is little more. And since we are computing the majority, and since the chance of majority keeps on increasing, okay, chance of majority keeps on adding up. And that's why the weaker algorithms together add up to give us the overall, give us a better chance. Okay, all right. So that's an important part. When we cannot have, when we cannot improve a particular algorithm or classifier beyond a certain point, we ensemble many of those. And also please note that if ensemble contains many different algorithms together having exactly same behavior, they are not diverse, then they will not give better prediction. Okay, right. So the idea is that given instance, let everybody do the prediction. Let's say there are 1,000 instances of tree. We feed we feed a particular instance and let all of 1,000 give the prediction. We know that all these thousands will give the prediction in terms of two classes A or B, right? And since all these thousands are uh, let's say weaker, meaning they are little bit correct as in little bit better than say the random, right? Therefore, the chance of majority becomes better. Okay, so that's the intuition around the ensemble. Okay, Ajay, did it make sense? All right, let me choose some better words. Or if somebody else wants to give a good example or want to question the belief or question my reasoning, I would love to hear that out because that would make me come up with a better reason, better answer. Okay, so imagine that we have 1,000 predictors. Each of them is like very weak because it out of 100 questions, 100 times it gives the correct answer only 51 times. Okay, that means it's a really weak. Okay, had it been 50, then you can't do anything about it because it's completely random. It's slightly bit intelligent than random, or slightly bit biased than random. So if we have thousands of such instances who are 51% accurate or say 60% accurate, when you sum up all of their predictions, they'll be correct 61% of time. And if you count those instances, the chance of majority is increasing, right? The majority is increasing. Majority is the 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 majority is summing up. Okay. I would love to answer it with more details. The simple thing is that if in a room you ask 15 people or 20 people about something which is right or wrong, the chances are if you do the probability calculation, then you will find that the answer given by a group which is um, which is made up of like different diverse set of people. If you conduct kind of a survey and then you basically draw the conclusion based on that, it is going to be more stable and better results than than otherwise. Okay, so okay, so there are we talked about multiple intuitions. One is the game show, as in Who Wants to Be Millionaire. Second, we talked about the situation in which there is a group of people who we asking group of people who we asking the question in the class or in a company. And third one, we talk about coin and so on. Okay, so those are the couple of examples, right? Right, right. So, and the theory is valid in the sense that we can actually experiment with even like simple classifiers, provided they should be diverse. Otherwise, there is no advantage. Okay, if they are not diverse, their outcome will be equal, right? If the outcome is equal, it's essentially how should I say? It's essentially like overfitting. We basically are doing the same thing over and over again and improving. I mean, we are not really doing anything better. Okay, so they must be diverse, only then you will get better results. All right, so now there's a very good argument for diversity in every class, in every group, and so on. You generally get better results. Wonderful, wonderful set of questions. So a question from Bintao was that what does F means? So here the intuition that we are trying to form is the think of tree as a function. Then when you feed an instance to the tree, this is the instance that we're feeding to the tree, we get the outcome. Okay, that's what. So we are feeding in F1 and F2, and we're getting in F1 we are getting 2, in F2 we are getting 0.9, and the overall is 2.9, right? So this is you can see that the probability is improving, right, by summing up. Though this one is predicting all very low, this one is predicting very high, but overall it's adding up. All right. Great. Let's move ahead. Now, very widely used, right? There are the tree ensemble methods are very widely used. You can take a look at random forest, gradient boost. Almost half of the data mining competitions are used by some variant of tree ensemble methods. So these are invariable to scaling of the inputs. Right? Unlike say the gradient descent, it doesn't the scaling of the input doesn't matter much. So it also learns the higher interaction between the features, as in nonlinear. and it can be scalable and are used in industry. So if we have like K trees and we have, all right, so we can always think of each tree like a function, okay? And imagine that we are going to create total capital F trees. So Fk is the function space amongst them. So you can always think of regression tree as a function that maps the attributes to this to this core, and parameters including the structure of the tree, right? So parameters which include the what is the parameter for the in the function? The function is function. The parameters are like structure of the trees, the score of each leaf, correct? How many leaves are there at each level, and the structure of trees, like what kind of decision nodes that we have created. That's the one parameter, and the other parameter is score in the leaf. Yeah. All right. So we can simply use like a theta of f1, f2, fk, and so on. So basically, we can say that the right. So we can just say each tree like a function, and then we can use that. Okay. Now instead of learning weights in RD, we are learning the way we earlier learned the weights in regression. In the same way, linear regression, we are here learning the trees. That's what is the regression about. Now, okay, a question from Tanmay is, so for ensemble method, we need stronger computing as a thumb rule. Correct. So what it does is basically these algorithms, most of them actually are going to be the computation intensive in many cases. And with ensemble, we can convert a very weaker algorithm into a bunch of smarter ones by combining them with other similar diverse ones, and therefore we can utilize the CPU resources. It will utilize the CPU resources, right? Therefore we'll need basically we basically convert the CPU power into good predictions. All right. So, and that's basically the idea. Okay. So, right, how can we learn functions? And so I'm just going through the presentation really fast. You should go through the documentation if you are inclined. Why I'm going through it? Because it's kind of a quick revision to for you in of the entire machine learning, and not entire machine learning, at least the basic part of it. So how can we learn functions? We define the objective, loss and regression, and optimize it. It's as simple as that. So we define an objective, which is a combination of loss plus regularization, and we optimize the objective. We minimize the value by tweaking various weights. So consider regression tree on a single input at a time t. I want to predict whether I like romantic music at the time t or not, right? So the model in the regression splits the data on the time t like this, right? If and so on, right? In the same way, if I can represent the same thing as a graph, there's a timeline and there's a prediction, right? This is right, the rate of right, the rate of how much I love the love songs. And so basically, right, this is how it looks like. Okay. So here the rating of for the love song was very low, but after after a person met the girlfriend, then it became improved, and then after after a while it again dropped down, right? And right, so okay, and after a while, as in right, mm, right, so things we learn is right, So basically this non-linearity, what we are trying to show is the non-linearity is very well captured by the by the by most of the decision trees. Okay, so okay, and yes, all right. So the objective of single variable and right, so it can basically handle all kind of non-linearity, specifically the decision trees. We've learned that part already, that it keeps on dividing it into these kind of steps. And okay, and how will the so objective for the single variable regression is combination of training loss as well as regularization. Regularization defines the training loss defines how will the function fit on the points. This is how well the function is fitting on the points. And how do we define the complexity? That is the regularization, meaning if we are having like too many split points, that means the regulation is just too much. Meaning if we have in addition trees, if we have number of trees too high, number of leaves too high, that means there'll be that should we be punished. Okay, that should be punished. On one hand, we should have great prediction. On other hand, we should have a simpler model. Okay, that's what is the sole idea. So if the user's interest is like this is the actual graph over a period of time, the graph looks like this. There could be this kind of graph, this kind of model whereby there's just too many splits, too many tiny splits, and this is having just too much of overfitting. Okay, and therefore this is not preferable, because here the sigma, the regularization term is really high. Okay, this we have already discussed earlier, so it's good that we are going through it. And then in this case, this one is, you know, the loss is too high because our function is not really good. This one is good because it's a best balance between it has minimum loss as well as there are less number of splits, so the regulation term is also low. Okay, so that's why this is kind of this is the part that we optimize, loss as well as the regularization, right? If we try to be very we don't want to miss any points and we end up creating too many borders, too many splits, then the graph will look like a complex one, and that should be punished. That should be punished a bit, and it should not be punished beyond what we are getting as a loss. Okay, so I hope this is clear. So in this case, the loss part is high. In this case, the regulation term is high, right? That's why both of these are not good. We want a good balance between loss, the loss as well as the regularization. All right. So okay. So yes, question from Tanwa is how regularization helps balance over overfitting and underfitting. Good point. So if you see here, this one basically is what? Is overfitting, correct? This is overfitting, right? So what's happening in overfitting is we have too many splits, okay? And when we say regularization, what it means is that we punish too many splits. We punish two things. One is total number of leaves, okay? If you have, and how do we punish? By adding the total number of leaves in the objective functions, okay? The way we were doing linear regression and we added the weights, the variance, I mean the sigma of all the weights, right, as the term, and we were trying to minimize that also. Here also, one is we minimize the loss, as in we minimize how much offset we are from the actual. We minimize the loss. Also, we minimize the number of splits. Okay. That's how regularization helps overfitting versus underfitting and bias versus variance. Okay. So this regulation term is something because we are going to minimize the summation of loss and the regularization term. So we're going to minimize both, which is a model which is not fitting, a model which is overfitting. All right. Tanmay, did I make sense? All right, great question. So we have an objective function in which there are two parts. This is the training loss. This is the complexity of the tree. So that's what is the overall objective function. And the possible ways to define the sigma could be the number of nodes in the tree, the depth, or maybe the total norm of the leaf weights, right? If we have just too many weights and so on, right? So so when we talk about decision trees, it is usually heuristic, right? We split based on our information gain. Remember the point that we talked about? We split based on the entropy change. The same thing could be the information gain. And we basically prune the tree. Right, prune the tree means we basically when we in the decision trees sometimes we basically once we have finished the tree creating the tree, we again go back to the tree and remove the nodes which have caused which have caused uh, which have caused the wrong outcomes. So that's generally pruning the trees, and also smooth the leaf values, as in have minimum number of leaves and so on. So in case of decision trees, we use the heuristics to first split the data based on what we have, and most heuristics map well to the objectives. Taking the formal objective view, let us know what we're learning, right? So information gain is basically minimizing the training loss, right? Okay. So when we have information gain, as in when we are splitting the data based on good criteria, we are minimizing the entropy. That remember that entropy loss or something we talked about earlier. We basically are minimizing the training loss, pruning as in we are removing certain leaves, right? That is improving the regularization. We basically improving the regularization term, right? Defined by a number of nodes. Max depth, again, it's a constraint on the functional space, meaning we are minimizing the overfitting. And smooth leaf values as in we basically bring down the weights at each leaf. That's again the L2 regularization on leaf values. So basically, these are the two terms we will work upon. One is the objective, as in the minimize the loss and minimize the regulation term. Okay, so we'll come up with those two parts and try to see how we can minimize the overall. Okay, that's the sole idea about the derivation. In the derivation, there are basically those are the two terms. We will try to come up with a formula which basically optimizes the overall loss plus regularization term. How to calculate complexity? Yes, complexity in case of a decision tree is how many splits do we have, how many total number of leaves do we have, what kind of height do we have, what is the individual weight, how big are the weights, and how many are the weights. Okay, those are the various terms that cause the complexity. Next question is what is omega? Omega, as in you mean this symbol, right? This is omega, yeah. This is omega. And yes, omega, or we call it sigma sometimes, right? This not here sigma, as in we've used the sigma term in case of a regularization earlier. So this omega is basically the symbol representing the regularization. Okay. So this one is the loss, this one is the regularization. So what we are doing here is we are going over each tree and summing up the regularization over all the trees. Okay, so regression tree ensemble defines how you make the prediction score. It could be used for classification, regression, ranking, and so on. This we talked just now, and it all depends on how you define the objective function. Okay, so you could do classification by changing the objective function a bit, and you could do regression usually, and then ranking also by just tweaking a bit. I mean, in ranking, we basically predict the order, which is same as just changing the regression a bit, right? And converting the decimal numbers into integer numbers. Okay, and let me see if we could cover a bit more about ranking. So we have there is the one random cut forest, right? That's what we had earlier. We talked about. Okay, we will cover these parts after the next chapter. Next chapter, that's the dimensionality reduction. Okay, so it all depends on how you define the objective function. We learned that the loss could be square. It's good for regression trees. And the logistic regression, the loss is this. This basically for the cases where we are trying to do predictions on classes. Let me turn off my phone. Okay. All right. Great. So, right. So what is the role of objective function? Objective function is something that we minimize. We minimize in order to get great results. Okay. So first term is loss that we minimize. Second term is the regularization term that we minimize. Okay. So when we are coming up with an algorithm, when we are creating a new fresh algorithm, these are the two things that we keep in mind. Okay. What is our loss function and what is our regularization term? So once we have come up with this, we'll permute over all the values of the input parameters or model, right? We will permute or we'll find those best model parameters that give us this objective function, the lowest value of this objective function, right? Either we do it using SVM or we do it using decision trees or we do it using the what was that? Using the gradient descent or and so on. So there could be many techniques involved, right? But the overall objective of most of the algorithms is to minimize this objective function, right? Meaning minimize the training loss as well as minimize the complexity of the model. Okay, that's the core idea. So that's the sole objective, to come up with great results. If we have a model which has minimized the training loss but has memorized the entire thing, right? Then what will happen is it won't be able to do great predictions on the production data. Therefore, the complexity of we need to punish the same algorithm, we are trying to make it really great at prediction. At the same time, we want to punish that algorithm for its complexity. Okay. Otherwise, what happens is it ends up memorizing everything and starts overfitting. Okay, so this part is for bring down underfitting. This part is to bring down overfitting. Okay, so that's as simple as that, the entire gist of machine learning, coming up with most of the algorithms. Okay, so bias versus variance trade-off is everywhere. Loss plus regularization objective pattern applies for regression tree learning as well. And we want predictive as in something that is giving great results as well as simple functions. This defines what we want to learn. We want to come up with the model and the objective. Okay, So in order to come up with the smallest value for the objective, we need to come up with the grid model. And how do we do that? Let's go ahead. Okay, so this is again, this is the objective function. Now, you remember we used the SGD, the stochastic gradient descent, or any gradient descent for that matter. The gradient descent can be used in the cases where we can we can tweak the weights by computing the derivative. If our individual functions are differentiable, then we can use the you can use the gradient descent. Gradient descent is a general mechanism in which what we do is we observe that what is the rate of change of error when we tweak the weights, and accordingly we change the weights. Okay, so at every value of the weight, we initially we assume some random values of the weights, and then observe whether the error is decreasing or increasing by computing the derivative, and then tweak the weights accordingly. So that's basically what gradient descent does. And here, in case of descent trees, we cannot use the gradient descent. Why? Because here what we are going to do is we are not going to tweak the values of weights. Instead, we are going to grow the trees. We are going to add or remove a leaf, or add or remove a tree. So that's what we have to do. So we take a tree, we add another one, and observe whether our objective is going up or down, right? And then we take another tree, then and so on. So if the objective is going down, we don't use this particular tree, as in the objective function that we just talked about. If it is going down, we don't use the new tree. If it is going up, we use the new tree. Okay, so we basically, that's what we're going to do. So, so the idea is to use boosting or additive training. We start from constant prediction, add a new function at a time, meaning add new tree at a time. So imagine that initially we have no trees, therefore there is no prediction. Then we have one tree. So this tree has given us some prediction, okay? And basically this tree, when we have one tree, then there is like there's no prediction from the previous one, and so on. Now when we have two trees, then at that point of time there's a prediction from the second tree added to the prediction from the first tree. Okay, so at the, let's say, t step, if we have t trees, right, so the prediction will be summation of all the trees at that point of time, correct? And this can be represented as the prediction by at t step is equal to prediction at t minus step plus the prediction of tth tree. So while this is additive, okay? Why this is additive? So at every step, the tth tree, we are observing whether our prediction is going. What is our prediction? Okay, so this is what is additive. So a question from Tanmay is that if we know the theory, is it possible to apply ML using other technology, R, SAS, ML? Of course, of course. So whatever we are learning, it's very much applicable to use R, MLlib, or SAS, because they all have the same function. They all have the same algorithm. It's just the way we pass the argument. It's just the way we receive the return value. Those are the only differences. Okay, so you will not have, I can assure you that you will not have any problems with respect to applying the same philosophies in other language, whether you're using like even in TensorFlow, even in the neural network, the same philosophy applies, and we will learn in detail that this objective function here this loss and the complexity is basically what we're going to balance in case of say a neural network. And the same the philosophy that we are learning now will remain valid there also. Okay, a very good question. Coming to the next one, At each step, a new tree is introduced. At each step, new tree is introduced. Yes. Okay. Now, a question from Ajay. Looking at the nature of ADA, does it apply better for the time series analysis kind of problems? What are the special class of problems it applies well? It's very similar to human learning. We are a sum of experiences and learning. Right, right. So, right, if you take a look at the AdaBoost or any of these trees, so I wouldn't say that it's specific to the problems like time series, but yes, it does solve those kind of problems really well. Also, also most of the decision trees, right? The adaptive boost or any of these decision like ensembles, right? They are pretty good with nonlinear data. All right. They're not, if let's say there's data which is linear, in those cases it doesn't work better than normal regression, but they do pretty well when it comes to the nonlinear kind of correlation. Okay. Okay, a question from Tanmay. My client is using R and soon going to cloud, so Spark MLA will be used. Right, right. So what happens is why before it's a good important question what Tanmay has asked. So what happens is when you are building a model, at times, what happens is you wrote it in, let's say, Java, right? Because you thought that will be more performant, and then soon enough you realize that the API that is available is uh, not great in say C sharp, right? Or some other language. So in those cases, you generally end up creating a separate service where you host your model, create a service, as in you make a call to that service and display it here. Okay, so that's also one of the choices. But if let's say in the code you are doing a lot of like data processing, churning the data, flattening the data, converting into proper columns, and like the way we did in end-to-end project, if that much code you have written for training, then what will happen is that code would need to be translated into another language. If let's say you wrote it using R and then you have to use it there, then there'll be a bit problem. But good news is that you can use MLlib using Spark R. So if your client is using R and soon going to the cloud where there'll be MLlib, you can actually translate your usual R code into Spark R. That'll be far easier. From within Spark R, you could use MLlib. All right. Great, great question. So moving ahead, and so far we have learned the right. Good. Now moving ahead. Now, so this is good. This also we talked about. So what we're doing is model at the training ground T is basically the prediction from the previous step plus the new prediction. Okay, that's what is going on here. Now, please pay attention. If you have any questions at this point, please ask. Okay, Ajay, Binta, Pavan, Praveen, Ravija, Robin, Shivam, and Tanmay. If you have any question at this point, please ask, because we're going to go more detail into this. So at any point of time, we are basically growing tree. We are adding more and more trees and doing the prediction. Correct? Now moving ahead here. So the question is, which function to add at any point of time? Which function to add? In simple words, we will optimize the objective. When we are adding a new function, it should not it should not impact it should not increase the value of the objective. It should decrease the value of objective. When we are adding a new function, our loss function should reduce, the loss should reduce, as well as the sigma should, the regularization term should reduce. If let's say loss is increasing by a tiny bit, but sigma reduces, that's also good, and so on. So therefore, these are the two summation terms. So whenever we have new tree, let's say we have a new tree, we put the new tree, compute the new loss by summing up the predictions, by computing the loss and including the prediction from the new tree, and then by computing the new regularization term, and so on, right? So we basically, when we have a new tree, the objective might go up, might go down. If it is going up, we won't use the tree, we use the another one, and so on. Okay, a question from Tanmay is that where are we assigning the weightage is like the example of young and so on, right? You are talking about creating a new tree, right? So that anyway is happening, right? Creating a new tree is happening just like what we did earlier. We're assuming that at every point we are going to create a tree. We basically do a other sample, feed that to our usual decision trees, let it come with the prediction. We basically feed that prediction to the loss and see how it is going up or down, and then since the new tree will have more number of leaves, the sigma will go up, right? And the regulation term will go up. And so we need to see that whether adding a new tree is decreasing the overall objective. Okay, if not, then we skip it and move ahead to another tree. All right, so that's a very the whole intuition around XGBoost. And so we basically optimize the objective in order to decide which tree to add. So essentially, this is the sole game in case of XGBoost, that instead of tweaking the weights, we pick which tree to add. Instead of like in gradient descent, in case of linear regression, what we did was we tweaked the weights, right? Here we are tweaking, we are choosing which function to add, okay? And that's basically optimizing the objective. So, right, the prediction at round T is going to be prediction from the previous round added by the prediction from this particular round, then this new tree. This is the new tree. This is what we need to decide at round T, whether to add T or not. Okay, so then again, objective is like this. So the loss of yi at any point, right? So yi with respect to the yit minus 1 plus the function value, this value, right? So loss of yi and yi hat at t step is what is basically our loss at this step. And then the prediction at t is basically prediction at the previous step plus the new prediction by this new tree, right? So here we have this function, and then sigma ft is same as. Now we move ahead. Usually we generally have the squared loss, right? The mean squared loss, you can say, but we just go with the squared loss and we square it. So we'll have the square of this one, y minus yi t minus 1, right? Plus ft and so on, right? So if we basically go ahead with this kind of model, so you will see that the yi minus yit minus 1 that we have anyway computed earlier in the previous round, right? Because here the loss, this loss of yi and yt minus 1 in the previous step, it was the objective at t minus 1 included the loss between yi remains same because the yi is the prediction Y is the not prediction, Y is the actual value, and this is the prediction. So actual value remains same in the previous round itself. So that component is removed from here. So it's ft square, the whole this term's square, like a, this is y minus yt minus 1, that's the a, minus ft, that's the b term. So the first term's square plus second term's square plus twice of this into this. Okay, so and since this one is a constant because we have already done it in the previous round, so yi minus yit minus 1 square is moved to the constant, and we are left with this objective function. All right, and this one is the residual from the previous round. We can't remove it to the constant because it's being multiplied with the ftxi. This is residual, and it's kind of, we have already kind of, it's constant. We can't do much about it because yi is the prediction overall, and the actual prediction, and this is the prediction from the previous round. We can't do much about it, so it's kind of a constant, and we can't remove it from the term because it's being multiplied by the new function. Okay, so if a new dd increases the objective function, we reject it. Correct. If new descent tree that we are adding, if it is impacting our objective function in like it is increasing this objective function, we don't use it. Okay, all right, is this clear? Right, so again, don't get daunted by the maths. It's actually not very hard. It's just simple symbols that are very hard. So at this point of time, we have the objective t. Okay, and the objective at this function, this is clear to all, that we are basically comparing yi and prediction at the tth step, which is equal to the prediction from the t minus 1 step plus the the tree that was added at the tth step. Okay, and then basically the regulation term from this particular new tree that got added. Okay, because the previous regulation term is anyway constant, right? We are not changing the previous term. We are not changing the previous regularization, right? So now, if you guys remember, there used to be something called Taylor expansion. Taylor expansion is an interesting phenomena in which we have like, if we are trying to compute the value of any function at a little uh, tweaked value from the previous, like x plus delta x, it's equal to f of x plus first derivative of the function with respect to x multiplied by the delta x plus 1 by 2 f double dash as in second derivative with respect to x multiplied by delta x square. So this is Taylor expansion from 1700s. It has been done like really long time ago, and basically this is a really important function. So it keeps on going, further and further. It's like 1 by 3 factorial. Here this is 1 by 2 factorial, 1 by 3 factorial f triple dash as in derivative 3 times x multiplied by delta x square. So you will notice that if you do that with e to the power x plus delta x, you will get the expansion of e to the power x. If you do it with sine x plus alpha, you will get the expansion of sine x series. And even like x plus 1, if you say the function is square and we say x plus 1 square, so it'll be x square plus the derivative of the x square, which is 2x, and delta x is 1, plus 1 by 2 into f double x, which is 2, because the second derivative of x square is 2, right? And then 1 square. So it'll be basically, it will be basically x square plus 1 plus 2x in case the function is x square. You should experiment with Taylor series, Taylor expansion in your own time. And this is a very, very important function. Also notice that in case this function takes multiple arguments, let's say it's taking y and x together, then that y will remain as such. Okay, so if let's say this function is taking one more argument called y, that y will remain as such, and it's only the expansion with respect to the term with which we are differentiating. Okay, so if we are increasing x and we are trying to do that, then we have to do the partial derivative with respect to x. Okay, not with respect to y. So this is clear. The Taylor expansion is clear to all. All right. So basically, when we come to this one and we basically do the same part. So here we are saying loss of yi with respect to this term, correct? So this is the Bain term and this is delta x. If you think of it, this is the x and this is delta x. And when we do the expansion, it looks like, okay, all right. Yeah, I'm coming to that, Tanmay. So here, what's happening is here, what we're doing is this is x and this is delta x. So we are computing the loss with respect to, we are expanding this series with respect to this x. Okay, so we are saying that uh, first derivative of loss function with respect to yt minus 1, okay, it will be computed, and that's what we are calling it g. Okay, and then we are computing the second derivative of loss function with respect to this, because this is our x, and right, so okay, let's say this is our function, right? Okay, so here this is kind of x and this is basically delta x, and our function is this, right? So the expansion of this one is going to be uh, let's just say that this is y, and right, so it's going to be right. So if this is our function, so it's going to look like f of y comma x plus delta x, right? This is delta x, and here here basically this is going to be this is comma, okay, so it's going to be f of y comma x, right, plus f of f dash of y with respect to x, and we call it multiplied by delta x. Then we have second derivative of f with respect to y and x, and multiplied by delta x square by 2 factorial. And then we keep on going like this, and the second derivative will keep on disappearing because it will become tiny and tiny. So after like couple of terms we can stop, right? There'll be third derivative, like we differentiate something 3 times and so on, right? But we can ignore those terms. So that's what is happening here. This one, I hope this is clear. So f of y comma x plus delta x is equal to f of y and x, and f dash like first derivative f with respect to x, and so on. Okay, so here that's what is happening. So we have given the name to this part as g, right? and this as H. Okay, so we have given that first derivative as the G and second derivative as H. So this one converts to something like this. Loss of yi and yit minus 1. That's the loss that we had earlier. So we can ignore this term as well. We can move it to the constant. We'll move it to the constant actually. And then gi as in the first derivative multiplied by delta x, which is delta brought by the new tree to us. This is that delta. And similarly, 1 by 2 h as in second derivative of the loss function, second derivative of the loss function multiplied by the square of the delta x, which is the change brought in by the new tree which we are adding. So every time we are adding new tree, this is the objective function that we need to compute and see whether it's making any sense. Now we can remove this loss term because this is something that we have already done. So that is already minimized. So we don't need to worry about this one because it is based on the previous number of trees which are already there. We're not going to touch the existing trees which are there. We are only going to figure out whether the new tree that we are adding is making sense or not. All right. So we have to find out the values of these parts and find out whether the objective is is increasing or decreasing because of these. Okay, so if you're not comfortable with this, think of the squared loss, right? And so on. Had this loss function that you have differentiated, had this loss function been a square, right? The way we do I minus y hat square, then the gi could have been what? Twice of this, and the hi could be the constant term. Okay, so that's what actually will going to be because we generally use the square only. Now, so we are removing the constants because we have already optimized this part. So we are left with this, okay? And gi is first derivative and the hi is the second derivative, okay? With respect to the yt as in the prediction. Okay, why are we spending so much effort to derive the objective? Why not just grow the trees? Know that what we are learning is convergence. So that's basically what we are trying to do is before adding a new tree, we are trying to figure out whether new tree addition makes sense or not. Okay, we want to do the we want to do that optimization right now instead of we just permute on all kinds of trees. We could do let's say 1,000 trees and then observe which ones are doing good and so on. So we want to optimize on that right now instead of later. Okay, we could have instead we could have just in a normal way what we do is we have like thousands of trees and we let them do the prediction with the belief that whatever they are going to come up with is going to be positive in the sense that as we said that it's going to be better than individual learners. We do that usually, right? But here we are kind of optimizing which tree to add so that our overall objective is reduced. We are doing both works, improving decreasing the loss as well as decreasing the regularization, right? Decreasing the regularization term as in the overfitting. So engineering benefit is recall the elements of supervised learning. In G and HI comes from the definition of loss function. The learning of the function depends on the objective via GI and HI. Think of how you can separate the modules of your code when you are asking to implement boosted trees for both squared and logistic. Okay, that's anyway okay. Because tomorrow if we don't want this loss function, we want some other loss function, we could generally just replace the function and we can compute the deterministic differential very easily. Okay, and right, we have already kind of discussed that part. Now we define a tree by the vector of, so generally what is a tree? Tree is something that has leaves and that has decisions in between, right? So we define a tree by a vector of scores in the leaf, and the leaf index mapping function that maps an instance to the leaf. Okay, so when we say tree, it means we have a function, mapping function, the weight of the tree, and we have like q, right? Q is the mapping function, which is mapping to the particular uh, leaf of the tree. Okay, so the x is basically we go with a's, then we reach here, correct? So those are the various values of x that takes us to the leaf, and eventually what we get is the weights. Eventually what we get is the weights, correct? So for each x, the weight is going to be different, right? The weight is going to be different. So this is what a tree is. We define a tree by a vector of scores in the leaf and a leaf index mapping function that maps an instance to the leaf. Okay, so the score on the leaf is weights, and the weights and that Q function, and so on. Okay, so that's what is a tree. Now, moving ahead, so we define the complexity. Now, this is some very important term. Okay, so whenever we talk about regularizing a tree, what we need to minimize, we need to minimize the number of leaves, right? And also the L1 norm, just like we did in case of ridge regression, we did the square, right? We did the square of the weight. So we minimize the weights on every leaf. The weight happens in decision tree. We basically go down till the leaf and return the weight, right? Those are the weights. Weights are on the leaf. So we basically want to minimize the weights just like we minimize in the case of linear regression. Okay, so we summation of all the leaves, the weights, as well as the number of leaves is what we are going to minimize, correct? So whether so good question, Tanmay. So other regulation term could have been the depth, correct? A depth. Now as depth increases, number of leaves increases. So depth and leaves are kind of relational with each other, are kind of having a relational with each other. But we can definitely do that because the height you can always compute from the leaves. Okay, therefore the height is not used here. Good point. Good point. I hope this is clear. So this is our regularization term, just like we used earlier in case of usual regression. Then we define the instance set in a leaf J like this. Okay. We define the instance set in the leaf like this because here in each leaf there will be some instance, the average of that one. So this is that. Okay, now coming back to that instance seed. So each leaf has some. Now this one has 3 instances, this has 2, this is 1, and so on. So ij is that set of instances in that leaf called j. In jth leaf, this I is a set of instances, okay, in that particular leaf. So here the I is nothing but the set of instances which basically qualify this function, meaning given xi, it's giving the jth leaf. Okay, that qualifying function same as what defines the tree's structure. So Q is that tree's structure. Now coming back to the objective function. So we have talked about the objective function being approximately equal to gi, the first derivative multiplied by ft plus second derivative multiplied by f squared divided by 2 plus the regulation term. Regulation term is this, some constant multiplied by number of leaves plus lambda 1 by 2 and then square of the weights. Yeah, again, this is right. I keep on saying it sigma, but it's omega. So it's basically sigma 1 to n GIFT, GIFT, the value of function, plus half of HI, F square at XI, plus plus omega, and this one becomes like the gamma t. That's gamma is another constant, and lambda is another constant multiplied by the total value of the weights. Okay, so I hope this equation is clear so far. Not clear? T is total number of leaves. And Wj is the total number of weights in each leaf, and there are total number of leaves as T. So we are summing up the weights in each of the leaves. All right? Yeah. All right. So, okay. All right. It might look daunting at first, but it's still manageable. Okay. Now here is the trick that basically the gist of the entire of this one, their algo is in this. Okay, so what they did was they defined something called instance set. Each leaf contains some set of values, right? Now, instead of iterating through all the instances like this, they are saying that first iterate through the leaves and then go through each of the leaf and operate on each of the leaf. So this equation that you see, the sigma, the summation over all the instances, has been kind of changed into this. So sigma of gi into wq, WQ as in the weights, right, has been converted into this, that go from leaf to leaf, right? Since each leaf has the same weight as Wj, then we don't need to apply the WQ. So WQ becomes Wj in each leaf because for every leaf, the total weight is identical, right? That's kind of, the tricky part here. Okay, so it's saying that, right? So what they do is they, instead of iterating over all the instances, the way we do is they go through each instance, compute the yi and yi hat, and subtract it from yi, and then come up with the value. Here, that's what was happening till this point of time. That go through 1 to n and all the instances, feed that to the tree, feed that to the new tree, compute gi, compute the weights, and so on, and then we count the number of leaves in the new tree, add that to this one. We also do the summation of over all the weights and so on, right? So that's what was happening till this point of time. But here, the same sigma can be written as like this. We go through all the leaves, and in each leaf, we sum up the GI values inside each leaf. Notice that for the whole leaf, the weight is going to be identical, right? For whole leaf, like here, there are many instances. Instead of we go 1, 2, 3, 4, 5, right? 5 instances, and keep on putting these instances in the new tree and see whether the loss is going down or going up. Or we could go from leaf to leaf. First we try this one, then try this one, then try this leaf. Correct? In the case of the third leaf, so this sigma will be like we compute the value of gi with respect to each of the instances, and then we multiply by the weights. Okay, so that's what is the very important part about it. Okay, this one is essentially representation of the loss function, and based on the expansion of the Taylor series. Why did we use Taylor series? Because we are trying to figure out the impact of the new function. Also, if we just used the square, if we just try to derive for the square, the mean square error, instead of a generic loss function, then we don't need Taylor series. We can simply convert our equation such that we just include the new terms and previous terms are anyway taken care, right? So Taylor series we used because that's what would make it generic. Otherwise, there was no point in using the Taylor series. All right. Now, all right, this is an important exercise because this is going to, uh, as in, give you the idea that a data scientist goes through the extreme limits in order to come up with something which is really optimized. Okay, and this was invented in 2014, and this algorithm has been winning most of the competitions. And I realized that not any of the classes around talk not and none of the classes around talk about this particular derivation, though everybody talks about how to use XGBoost, but nobody talks about this. So I thought it'll be important to discuss it with the session. Okay, so here we basically converted from going from instance to instance, and we go from leaf to leaf. All right, so let's take a break. And I think this is pretty much it. There is one more step after this, and that'll be good enough. Okay, let's take a break for 10 minutes and back by 8:47 a.m. IST. Thank you, Binda. Please post the time in your time zone. All right, so I'm back. Should we start now? All right, so all right, so here is a interesting part. So basically, where we basically were trying to figure out the loss function here. And instead of just using the mean square error, we tried to do it for generic, and that's why we ended up using the Taylor series. We did not need the Taylor series at all. In simple words, we could have just used the loss for the x plus 1, and we could have actually eliminated the previous term. The idea was to, one, eliminate the previous term because we have already computed that, and we are trying to measure the impact of new tree being added. Okay, so we could have just used the normal MSE, and we did not need to do the differentiation and all of that. Okay, in very simple words. Okay, this HIGI is just making things a little more complex. Probably we could eliminate this entirely in this discussion. We could eliminate the Taylor series entirely if we just keep keep it focused on mean square error. Okay, if we keep it on mean square error, then we'll know how to expand the series with one more term, and that could have been good enough. All right. So I'll just give you an idea what I'm talking about. So if we have like x plus 1 square, right? We can do the expansion ourselves, right? We can do the expansion like it's like x square plus 1 plus 2x, right? If we are saying that f of y and y this is hat minus 1 plus the right, this is if this is a lot function, this is our tree, and so on. So this would become pretty simple. It'll be like y minus the y hat from the previous step plus the new tree that we have added. This is new tree, okay, and the whole square, right? So this could be written as y square plus the square of this term. Actually, we could take this out in the other way. So we could say y minus yt, y minus y hat t minus 1, the square of this one, plus f of x, whatever is our trees values that are coming up, that plus, sorry, the minus 2y into y hat from the previous step. Then we don't really need then we don't really need the Taylor series. So this is not needed because this is a constant. We have already done. This is basically difference between the actual value minus prediction from previous before adding this new tree. This is the prediction from previous ensemble, and this is the value from the new tree that we have added, the square of it, and then twice of y, right? Twice of y minus yt, something of this sort, into f of x. Okay, then we wouldn't need all that differential and all that. Okay, so this is what it is. So f of x square plus twice of f y minus y hat. Uh, this is the prediction from the previous value. This is the delta between previous value and this, and into f of x. This is the current value. Okay, this is a constant, the residual term. This is the current value that's being predicted, and so on. So had it been just mean square error, we could have simply done that. Okay, and if we do that, it'll be easier to visualize, because this g and h are unnecessarily causing it a little complexity. Okay, so yeah. So far, we are all okay. We basically, what we have done so far is we have eliminated the impact of the the previous trees. We basically converted that into constant, and we have isolated the impact on the objective function because of the new tree that we have added, right? And then we basically added a regularization term. It's basically something which we came up with, that okay, let's add the trees, let's minimize the leaf. So why don't we just add it to the loss function, and to make that an objective function. Okay, so we added the number of leaves and also weights, just like logistic or regular regression. And then this is one step that is important in this case. So instead of iterating over all the instances, we are iterating over the leaf. And for each leaf, we are computing the first derivative of the GI, okay, and multiplied by the weight, because for each of the leaf, the weight will be the same. If there are t leaves, then there will be t number of weights. All right, and so on. So then we basically, once we converted this summation per leaf, then we can bring this term together here, correct? So here, while hi is also per leaf, here this we summed it up per leaf plus lambda by 2, right? Because now both this as well as this are both are over the leaves. So for each leaf, this is what is happening. All right. So T is the total number of leaves in the new tree. Okay. And weights are in the new tree, these are the weights, and so on. So this is what is happening. And also the instances are fed to the new tree in from 1 to n, all of these. Okay, now here is an important question. So if we mark this as capital G, the summation of small g, which is basically the the first derivative of the value. So the summation of g and summation of h, if we mark it as capital H and small capital G, then the equation looks like this. Okay, capital G and the capital H, right? This is how it looks like. Now, what is the minimum value of this one, right? That's what it is. So if we have gx plus half of h x square, what will be the minimum value of this one? Anybody? How will we compute the minimum value of this one? So we have gx, let's say g is constant, and half hx square. Again, h is constant. What is the minimum value of this one? Correct. So we'll basically do the differentiation will be g plus 2 of hx, correct? And equals to 0. And that will bring us to the point that the the right that will be basically that will bring the g bring a relationship between g and h. Okay, and when we put that back here, so h is going to be equal to so x is going to be equal to the g by h minus g by h, and when so x is going to be minus g by h, and when we put that value, it's going to be g squared by h minus 1 by plus 1 by 2 g squared by h. Okay, so that's how it's going to look like, and essentially this is what it will turn out to be. So the minimum value of this is half of g squared by h. Okay. Yes, since both the terms here, this term is once we differentiate it. Good point, very good point. Thank you, Tanmay. So once we differentiate, do the first differentiation, we'll get g minus g plus 2x, and when we do the second differential, it'll be positive, and therefore when we do the second differential, it'll be positive, and therefore this is the minimum value. Okay, so yes, you can try that out. So second differential has to be positive in case if we are trying to minimize the value. If we are trying to maximize the value, second derivative has to be negative. Yes, correct. So what if we have a local minima? So local minima is hard because it's a convex function. If you take a look at this, it's a convex function like a parabola, and therefore the local minima is difficult. And if you have local minima, there are multiple local minimas. Generally, in those cases, this equation would have like bigger degree, more degree, and therefore solving the derivative of this one becomes really hard. All right, very good questions, very good questions. Let's keep going, and if you have any question, ask me right now. Okay, so right now what we did was we basically replaced this value with something like this. Okay, so the objective function has become extremely simple. The objective function, after substituting this here, it became 1 by 2 sigma over the each leaf. We are iterating over the leaf, and then we are putting this here. We are saying here in this is like oversimplification of this one. Okay, where x is wj, g is gj, and h is hj plus lambda. Okay, then the answer was 1 by 2 g squared by x, and the same way here the objective function will become 1 by 2 capital G square by hj plus lambda plus gamma t. This is our objective function. All right, so all we are saying is that compute the derivatives over all the and sum up over all the values inside the leaf. Okay, compute the second derivative of the loss function and do that inside the leaf. And we don't really need to compute the derivative because the loss function is straightforward. And and then right, so we basically compute the values for each instance inside the leaf in a new tree. So we iterate over the new tree, go over each of the leaf, and compute capital G and capital H, and then see whether this objective function is minimized. Is it going to be negative or positive? or or this objective function is smallest, okay, and so on. So this is our objective function. All right, and the weights the weights on jth node would be equal to this value. Okay, so this is our objective function, and that's what we do. Okay, so all right, so so essentially what we do is the smaller the score, the better is the structure. Okay, so at every point of time when we are adding a new tree, we basically compute this objective function overall, all the leaves, and then if the score is smaller, the better will be the structure, and that's what goes on beneath this. So again, so enumerate the possible tree structures Q. Okay, calculate the structure score of Q. This is the structure score using this function, and find the best tree structure and use the optimal leaf weight. Okay, but there can be infinite possible tree structures. All right, so there could be infinite tree structures, right? So in practice, we grow the tree gradually. We start at the tree at depth 0. For each leaf node of the tree, we try to add a split. Now here what they have done is since it is done over so it is done over leaves. It's the important part. So even though we started our whole derivation from enumerating over all the trees, whenever we are adding a new tree to ensemble, whenever we are adding a new tree to ensemble, we basically are computing the impact on our objective function. Okay, that how much do we gain or how much do we lose because of adding a new tree, right? Then we turned our equation towards iteration over the leaves. So instead of enumerating over all possible tree structures, so when we are adding a new tree, always there's a question that which tree should we add. And if you try to create all possible tree structures, like in decision tree, we could divide it based on one partition, then another partition, and then so on. There could be infinitely possible tree structures. So we can't really do that. Instead, what we do is, since our objective function is is basically dependent on the leaf computation, we can actually grow a tree stepwise. We basically create a leaf, compute the objective function, and for the left and the right, and see if we can further grow the tree or not. If we are further growing the tree, then are we having an information loss or information gain, or by computing the objective function. So this is a very interesting part whereby adding a new tree has been replaced with growing a tree. Okay, so what we can do is we can start with the tree at depth 0, and for each leaf node we are adding or trying to split the change. We observe that, okay, because of adding new two leaves, this is what we are going to gain. This was our objective function before splitting, and this is our objective function after splitting. So because of adding this new tree, we could add two trees. One is, okay, uh, all right, so let me just draw it. Probably that'll make more sense to you. Okay, um right, so let's say we have an ensemble. Let's consider this as a black box. Okay, so we could add one tree like this, okay, to this one, or we could add one tree and having two branches with it. Okay, in this case there is one leaf, there is two leaves. So question is that, right, first by moving from here to here, is our objective function changing? So we compute the objective function because of this one. We compute the objective function because of this one, and we subtract. This is 1 and this is 2. This is objective function O. So we subtract the two and see whether in this black box moving from objective 1 to objective 2 is making any sense. That's what is happening here. That's so this is that previous one when the capital G and capital R of the left hand side were basically total, right? Divided by HL and HR, because all of the elements in the same were in the same node, therefore the value was this much. And this was the previous value, this is the new value, right? And gamma t, because the since we are increasing the tree by nodes by one, earlier there was one leaf, now there are three leaves. So right, there are three leaves, and okay, so it should be like 2 into gamma. Okay, 2 into leaf. So there was one, no, there are two, correct. There are two leaves. There was one leaf now here and two leaves here, correct? Because this is no longer a leaf when we added two children to it. So the total number of t is actually 1. Therefore, gamma t is like gamma. So this is what it is. So we basically increased the leaf by 1, and therefore, right, therefore the -1. Okay. Yeah. So here this part was negative and this part was positive, therefore here is the minus. Okay, so that we have just converted it. All right, so all we do is basically we came up with this clever objective function that given a leaf we can compute this, and if we sum up over all of the leaves we will basically get the overall objective function. If the summation is smaller, then we will get the good next step. Okay, so instead of enumerating, figuring out all possible tree structures that feeding it, here the second step, very clever step that was done was that we basically start with no tree, then add one leaf and observe what happened. Then we add more leaf like this. And here we are trying to, figure out whether splitting a node, makes sense or not. Splitting a node makes sense or not. Okay, that's what is happening here. All right, is everybody clear? So we are essentially growing a tree instead of adding a tree. And that's a cleverest part in this. We converted our equation from iterating over the instances to iterating over the leaves, and then we basically converted we figured out that the objective function between we can compare the previous step and the next step, as in if we split a particular node, it increase the objective function's value or decrease? If it is decreasing, then we grow, otherwise we don't. All right, so at any point of time we'll be able to figure out whether to grow the tree or stop it then and there and go to the next tree. All right, I hope this is clear to you. So we compute the score on the left child, score of the right child, score of the node. If we did not split, this was the score, and we subtracted the left plus right minus this one, because overall objective basically goes over each leaf, right? Leaf 1, leaf 2, all right? And this one is no longer leaf, and so that's what is going on. So all right. So other question that is remaining is, how do we find the best split? Okay, how do we find the best split is basically just go over all the values, all the feature values, keep splitting, figuring out the objective gain, whether we are gaining or losing, and then essentially if we are gaining, then we move ahead, and if we don't gain, we leave it as such. and move to the new tree. All right. A question from Tanmay is, what is the value of the complexity cost? What is the value of complexity cost? As in the loss function, right? This one, the omega one, right? This is the complexity. So here, what has happened is when we are splitting a leaf, the weights are going to be same. Okay, since it's the same weights that is being distributed, therefore the last term that we have here, right? Just a second. No. So what's happening is, yes. So what we have done is we have figured out the optimum value of the weights. Okay, this is the optimum value of the weights. That is good. So wi was this one. So we have eliminated that term here. Okay, you mean this one, the complexity caused by reducing additional leaf, gamma, this gamma one. So this is a constant, the gamma one. This is a regularization parameter that we can feed in and do the hyperparameter optimization. All right. So this is how we find the best split. Okay, and what is the gain of a split rule? So what we do is, let's say we have this is where we are splitting. Let's say we had these 5 instances. This is where we are splitting. We compute the g and h of this one, the first derivative of loss function and second derivative of loss function. It'll be like 2 into y minus y1, right? That's the prediction. And this will be the only constant as 2, and so on. So we computed the left side and right side, and okay, so yes, so essentially we will basically, for each of the predictions, whatever we are deciding upon, let's say whatever splitting we're deciding upon, we will get the loss, first derivative of the loss, which will be 2 into y minus y1, and this will be the second derivative, which will be constant, and this will be in the same way. So we compute the left and right, and right. So what we are going to say is that here we are going to iterate over all the features. Let's say that feature here is the age right now, and all we need is sum of g's on the left hand side as well as h on the left hand side as well as right hand side, and we can compute the gain. This is the gain if this is positive, which is inverse of the objective function. If this is positive, then we go ahead, right, or we basically can also iterate over all the gains and figure out what is the maximum gain we can get. Okay, we can basically left to right, we do the linear scan over the sorted instances and have to decide the best split along the feature. Okay, so we can do that. We can basically go from left to right, figuring out uh, just we figuring out which one is giving us the best gain, and then we get the best results. Okay, we basically pick the value, pick the point to split the leaf where the gain is maximum. All right. A question from Tanmay is, do you have some cheat sheet where we can readily refer to the case studies, like which scenario is generally best suited for which kind of algorithm? All right, this is actually somebody has also asked me yesterday, and probably will try to do that. Okay. Okay, so I'll see if we could do that, or I'll just share the Google Docs with you in case you also want to contribute. All right, so all right, so we basically have left to right linear scan over sorted instances to is enough to decide which feature to split on. Okay, so for each node, enumerate over all the features, and for each feature, sorted the instances by the feature value, do the linear scan to decide best split along the feature, take the best split solution along all the features. Okay, so the time complexity growing a tree of depth k is going to be this much. Okay, where n log n is going to be time to sort the data multiplied by d and k. K is total, k is basically the depth, and there are d features because we are iterating over each feature, sorting the data and doing it again and again for every depth. Okay, so that's what it is, right? So we'll take all the values, sort it based on we'll pick one feature. We'll pick one feature, and then we'll pick one feature and then sort the data, right? And then we'll go to the next level and do the same thing, and we'll keep on doing that. And this can be further optimized using the approximation or caching of sorted features, and so on. And it can scale very well on very large data sets. A question for Minta is, why does the optimal leaf, right? Uh, weights have such a formula. Okay, why does optimal leaf weights have such a formula? Okay, so which formula? This one, right? I'll talk about this one. Okay, this one. Which one are we talking about? This one, you mean? Ah, I see, I see. So see, in this case, let's say, let's talk about this case, right? Or let's say, uh, if let's say X was W, and H was, okay, and let's say this is the case. All right. Let me see if I could draw something. If let's say this was A, and this was B, and this was X, correct? So it'll be AX plus bx square by 2. What is the minimum value of x for which this value can be minimized? We differentiate it. A plus bx equals 0. So x is minus b by a, correct? When we differentiate it and equate it 0. Now, right? And then if you take a look at this one, right? Yeah, you're right. It should be a by b, not. So x is going to be minus of a by b. Now, what is x? X is essentially wj. So wj is going to be equal to a is what? Gj divided by hj plus lambda. All right. So that's what is going on, and right. So that's what is going on. So basically can be done on large data set. Okay, so other questions, you can take a look at the presentation. You will get really good mm, ideas about the XGBoost. There are a few more ideas in this, like right. So also sometimes instead of just adding it like this, we put an epsilon called shrinkage. Remember the shrinkage we talked about? Instead of just simply adding it, we put an epsilon, and that's another thing. Okay, so you should take a look at the presentation, the URL which I've shared with you. So that should give you an idea. All right, so that's pretty much about the about XGBoost. Okay, right. There are a couple of more things to talk about. So, all right. So essentially, the objective function in the end is this. Okay, and so on. All right, that's what is going on. So parameter tuning in XGBoost is dark art. The optimal parameters of model can depend on many scenarios, so it's impossible to create a comprehensive guide for doing so, right? So first of all, we need to understand the bias variance trade-off. We have already talked about this. If there is bias leads to a simple model leads to a bias, while complicated models lead to variance. Okay, the underfit versus overfit and so on, right? So we will talk about naive Bayes and after this. Okay, we'll talk about towards the end. All right, so that's basically what we have talked about earlier. Then there are two ways you can control overfitting in XGBoost: by controlling the max depth, minimum child weight, and the gamma. The gamma is the one which was being multiplied with number of leaves. Okay, and add randomness to make training robust by noise. This includes subsample and column sample by tree and so on. Okay, so there are many parameters, so it's not so easy to actually come up with some good parameter tuning in XGBoost. Okay, so the parameters of XGBoost, I have like 3 categories, and the first one is general, and other is the booster, and third one is the learning task parameters, and so on. So a question from Tanmay is, do we have NLP? We had like basic NLP in deep learning part, but I think we will expand that a bit. Okay, so that's the point. Now, basically, these are various kind of parameters in XGBoost. You could give it a shot, try them and experiment, and just go over the parameters. The idea in the end is that you generally do the hyperparameter tuning. You don't really get uh, you know, so lucky all the time that you really can't come up with right, come up with all possibilities by yourself. You leave it to the hyperparameter. So some of the things that seems to work is this, right? So you could tweak this and see which one is working for you. All right. Similarly, for some people, this kind of parameters have worked. So this is what I picked from Kaggle. That one seems to be working for people. So you could try a similar or a slight deviation from this one, and you will get a good results. Okay. So experiment with XGBoost when it comes to classification or regression. And here are some of the documentations which you can go through, and you will get a good picture. All right, so that was XGBoost. Okay, though we did not have planned to go this deep, but I thought that it will be important because it's kind of you know, a mystery to many people, and also we wanted to eliminate the fear of the symbols and the maths. Okay, so that's why I thought I'll go over the XGBoost. All right, I hope this was useful to you. All right, so a question from Tanmay is, the sentiment analysis come under NLP? Yes, so sentiment analysis has many facets. One of them is statistical one, which is extremely simple one. That for that you don't really need to know NLP. We will talk about something that is the very important aspect of NLP called the called the called the word to vec or glob vectors. We call them, why am I slipping the name? We call that word embedding. Okay, so we will talk about how to create word embedding from the text using the neural network. All right, using the neural network, we will learn how to create the word embedding, and that's the most interesting phenomena in the deep learning, in the NLP. Okay, and because that has changed the entire landscape of the natural language processing. Okay, so we will cover that part, and we'll understand how exactly it came into play. Okay, as part of deep learning. All right, the next thing I would like to discuss with you is dimensional reduction. Dimensional reduction is one of the very interesting part where we will understand how to reduce dimensions. A question from Tanmay that do we have a project on Twitter sentiment analysis? Not in this one, but in the last one, what we have is a project on given a text, how do we create word embedding? All right, that's the project we have. We will cover that in more detail this time. And we can use those word embeddings to do sentiment analysis, to do various other kinds of tasks. Also, we have a couple of more projects in the NLP. One I created for creating automatic quizzes. I used some libraries. That one is available under ML. I have created a project under my repository saying it's called auto quiz. So you could take a look at how we can create the questions automatically using the NLP. All right, let's. I think it's important. It's the important point you're trying to make is that let's cover NLP in bit more details. All right. One is like using the statistical means, and then we're using the deep learning kind of thing. So probably I'll keep the NLP towards the end after the deep learning. I hope that's okay with everyone. Right? Is that okay if we keep deep learning towards the end after we have done with, sorry, if we do the NLP after deep learning, because we need word embedding and other techniques to get started with NLP. Yeah. Bintao, Pavan, Praveen, Ravija, Robin, Shivam, and Tanmay. Should we do that towards the end after deep learning? All right, great. All right, so moving ahead with a very interesting chapter called dimensionality reduction. Dimensionality reduction is again the art in the case of machine learning. All right, and you'll find that when it comes to solving real projects, okay, say I was working with a friend from, say, uh, one of the scientist friend who is doing some material science research in one of the premium institution. I don't want to put the name. And there he was trying to do a kind of image recognition. And the moment I looked at the image and we were trying to do the usual one, like MNIST one, the way MNIST is for classification, we were using a similar technique, similar to how we solved MNIST. I was using a similar technique and it wasn't fitting into the memory. Okay. And then I realized that most of the pixels in the image are useless. Okay. At that point of time, this knowledge of dimensional reduction came into play, right? Though, and if we what I found is that if we do not understand the every aspect of machine learning, what happens is when there is a slight deviation in the problem statement, or when there is when something is not fitting into the memory or something is not optimized, then we kind of lose hope if we do not have the understanding of the subject. All right. Same is the true in case of dimensionality reduction. Dimensionality reduction would come into use whenever you are trying to solve any machine learning problem. Okay. The way, whichever algorithm we use, we can always ensemble it. In the same way, the dimensional reduction is a generic skill or generic knowledge which will be applicable not only in case of the not only in case of machine learning, but in other cases also. We learn something really interesting about about any object. All right, we learn something really interesting, like for example, if you have to compress a video, right? What can we do? All right. Like for example, I was trying to figure out, can we link the slides to the video? Given a video and the images of slides, can I link it? At that point of time, the knowledge of the dimension reduction comes into play. Okay, so dimension reduction is a very important aspect. It is used in machine learning, in compression, in signal processing, and so on. All right, so we are going to talk about dimension reduction in more details. All right, some problem sets may have large number of features, making the model really complex and slow, and even it could make it impossible to find a solution. Right? For example, if you are realizing that you can solve something using the normal equation, and if it has many features like in a pixel, like in an image screenshot, it has a million pixels, right? And that makes it impossible to solve the problem with related to the dimensions. Okay, so a lot of times number of columns or number of dimensions makes it impossible to solve the machine learning problem. This is called as curse of dimensionality. Okay, now, for example, MNIST dataset, each pixel was a feature, 28 by 28 number of features in each image, and the the border, like these pixels around, you can see how many percentage of pixels are these. These would be around like 50% of pixels are kind of useless, right? So half of the memory is kind of misused. Okay. Also, the neighboring pixels, these neighboring pixels are kind of highly correlated, right? So neighboring pixels like this and this are very highly correlated. This and this are highly correlated. So generally, the neighboring pixels are highly correlated and can be merged into one without losing much information. If the same thing would have been like 1,000 by 1,000 number of features, it'll have 1,000,000, 1,000 by 1,000 dimension, it will have 1,000,000 pixels, and 1,000,000 pixels is just too much. So, so, in these cases, the dimensionality reduction plays very important role. Okay, so we could not only remove the pixels which are not in use, but also could merge multiple pixels together, hence further reducing the dimensions or features. All right, some benefits of dimensional reduction is faster and more efficient model, better visualization to gain important insights by detecting patterns, and the drawbacks are lossy. We lose some amount of information, and what we will learn is, as part of this session, is we will figure out that how to decrease the dimension, by minimally removing the information. Okay, so whenever we, let's say, look at an image, if we compress it, right, or we zoom it, a lot of times zooming out as in decreasing the size, sometimes seems to decrease the information, but in reality, it does not. Say, for example, an MP3 song, a song of 60 MB and 3 MB, if you hear both of them, you can hardly make a difference, right? You can hardly make out a difference. And that MP3 song has been one of the biggest innovation in the music industry because it brought down the size of a song from around, say, 60, 70 MB to 3 MB. That is 20 times. That suddenly reduced. That suddenly reduced the overall, right? That suddenly increased the reach of a song over the slower internet and so on. And that's where the trick lies. What we learn is we will learn how to keep the information while losing some information without worrying about actual loss. And my question is, how is it different from removing outlier? We've learned that in case of removing our outlier, we remove the instances. Here, we are removing the features. All right. All right. So I hear a lot of people talking about more than 3 dimensions, right? I hear like people talking about many dimensions. They understand, like we also, you will find that we ourselves would tend to demonstrate, to tend to talk about there are so many features, so many dimensions, even like I'll just turn on the camera. So even like in the case of MNIST, right? We had around 800 dimensions. Okay, though we were able to solve the problem, but we really don't have a clue about how do things look like when the dimensions are more than 3, right? It feels that we understand more than 3 dimensions because we are able to create features, we are able to subtract the distances, and we are able to come up with these formulas using NumPy, which can, handle all kinds of dimensions. But in reality, as human, we hardly understand the meaning of more than 3 dimensions. Okay, the meaning of more than 3 dimensions. All right. So let's see. As in, though we mathematically can come up with the ideas in multi-dimension, but visually, it's very hard to deal with more than 3 dimensions for us. All right. Let me ask you this very simple question. Question is, if you are, let's say, taking a square, okay, we are taking a unit meter square, and it has a 1 millimeter border. Okay, what is the probability of choosing any point on this square such that it is on the border? Okay, border's thickness is 1 millimeter. So what is the probability? Let's say we have a square, and we have to choose a point on this. What is the probability that this point is going to be on the border? Anyone? Okay, the answer is simple, that compute the area of the border and then compute the area of the overall square and then divide the two, right? We're talking about square right now. Yeah, go ahead. Anyone? Yes, it's around 4 divided by this value, correct? And why we have said this much? Because we multiplied it by multiplied it by 100. Okay, So 1 minus 0.998. This is the area of the the surrounding border. All right. I think it'll be 0.004. Is that correct, Shiva and Ravija? The area of the border. All right. So this looks good, right? Now, let's say we have a cube, 1 meter cube, okay? A cube of 1 by 1 by 1. What will be the probability of hitting the border? What will be the probability of hitting the border? Okay, or choosing a point which lies on the border. Anyone? Right? My next question to all of you is, we did it for one, okay? We did it for square, let's do it for cube. What will be the probability of hitting the border in a cube? So the volume of, or you can say that when we choose a random point in a cube, in a 1 meter cube, what is the chances that it is within 1 millimeter of the border? So the volume of something that is 1 millimeter from the center, okay, is going to be on this line, right? So all you need to do is find the 1 millimeter shell in case of a cube. That's going to be here. They're going to be cube. Okay, so 1 minus that cube. Okay, so in that case, okay, in that case, how much is that going to be? Let me just launch. Let me just launch this. Okay, so we are talking about 1 minus and 0.998. That's the dimension. Okay. All right. Now it is 0.006. Okay, in case of a cube. Are you convinced? So earlier it was 0.004. Now it is 0.006. You see that? The chance of something being on the edge is higher in case of 3 dimension as compared to 2 dimension. All right, does it make sense to you? Or is there something wrong in the formula? Yes? All right. Okay. Okay. Good. Very good point, Tanmay. Intuitively, it makes sense because there is more border area. Anybody else? Yes? All right. Now let's increase this to say 10 dimension. Now you can see the chance has increased very much. And if we have like 100 dimensions, the probability of hitting the edge is 0.18. Now, what does it mean to you? What does it mean to you? If you further increase it, if you have like 1,000 dimension, then every point you choose, the chances are it's going to be on the edge, right? It's going to be on the edge. So when we are increasing the dimensions, we are, and yes, let's just try with the 10,000 dimensions. Okay, let's just try with 10,000 dimensions. So it's like 99%, right? So that's the important part. That's the important part. So what's happening is, as we are increasing the dimensions, right? Almost everything is an edge. So no matter where we put the dot, it's going to be on the edge. Now it doesn't make sense from the visual perspective. I can't imagine how it looks like. The more the dimensions, bigger the edge, and so on. So it's basically, so, right? And some more important facts. So as we do more these, this, if you think about it, it doesn't seem to make sense to us visually that how will a cube of 10,000 dimension will look like, right? How will a cube of 10,000 dimensions look like? Though we are able to visualize that in an Excel sheet, we have 10,000 columns. Those are the features. Those are the features of every record. Those are the dimension of every instance, right? So even though we are able to make sense of it in terms of features, but when it comes to dimensions, we hardly can visualize it, right? So we like when we are, say, observing something, we can always easily visualize its height, width, and thickness, but we can hardly visualize the other features as other features of this as another column. So those are the basically features. And when in the similar way, when you have 10,000 dimension unit meter square hypercube, what will the borders look like? We have no clue. All right. So this is where our intuition doesn't work. This is where our intuition doesn't work. So in many times you will find that our intuition may not work well when it comes to the higher dimensions. Now imagine that we pick two random points on a square. The distance between these 2 points is going to be roughly 0.52. If we are going to pick 2 points randomly on a unit square, the distance between these 2 points shall be roughly 0.52. Okay, and you can basically just do a bit of calculation and then figure this out that this is the case. But if we pick 2 points randomly in a million dimension hypercube, the distance between these 2 points shall be roughly this much. Okay, so you can also see that the, imagine that imagine that there are two data points A and B, then each one is on opposite dimension, then the distance will be between 2 points will be the other extreme and this extreme. That's going to be like distance from center is going to be 1 square plus 1 square plus 1 square and so on, right? In that case, if you have 2 points randomly picked from a 1,000 dimension hypercube, the distance between these 2 points shall be roughly this much, which is really huge, which is really huge. So higher dimension data sets are, okay, so I'll talk about that later. So the important part is that at number of times we may not make sense of out of higher dimensions visually, but mathematically we can always make sense out of it. Okay, and that's where the maths comes into play, that we see things which we can't visualize. All right, we kind of do the calculation over things which we really can't visualize at number of times. That's what happens even in XGBoost, that at a number of times we were not able to visualize what's going on, but we were able to differentiate and equate it to 0 and find the value, right? So that way. And okay, though at number of times we can solve many problems really easily, many problems really easily. Let me ask you a simple question. The same question can be done two ways. Okay, one is using like the differential calculus, and other is using the using visually. Imagine that you have a cube. Okay, imagine that you have a cube. Okay, okay, all right. There is some sweet on this corner, and the opposite corner there is an ant. There is an ant. Okay, and this ant wants to go to this corner, or you can say ant is on this corner and the sweet is on the other corner, and ant wants to go to this other corner. All right, so this ant has multiple options. One, it can simply just go down here and then walk. It can't really fly. Okay, so now you have to find a way to tell the ant that this is the path you need to follow. And let's say you are given A, B, and C. These are the three dimensions of this. And you have to find out which way the ant should go. All right, you can consider this as 10, 20, and 30. First, try to solve it with equal dimensions. Then you can change. Okay, when you do that, right, so you will find that there are two ways to solve it. One is visually, other is by the way of using maths. Okay, you can actually give it a shot and then we can talk about it. So the idea that I'm trying to drive to is that there are multiple ways of solving a problem. One way is visually, and other way is doing it using maths. So in case of let's say you got an image of image of, let's say, MNIST dataset. We could look at each image individually and see that okay, these corners don't look too useful, so let's remove the corners, right? While the other other strategy could be to mathematically drive the points which are useless in the images by looking at all other images. If there is no change at those points, we can remove those points and so on, right? So that's basically the multiple ways of solving problems. And specifically in case of dimensionalities, you'll find that the visual ones keep on forcing us to think, all the time, that to visualize things. Dimensions force us to, uh, you know, we try to visualize how does the data look like. While at number of times we'll have to do the mathematical way, and is more accurate. A question from Bintao is, why is the distance between 2 points a unit on a unit square? So the distance between, if we pick 2 points randomly on a unit square, right, the distance is going to be roughly 0.52. Okay, so all right, it's a harder question to answer. Let me think of a possible answer. And right, essentially it's an empirical number. We basically have computed, let's say, 50 points uniformly spread over the square, and then found the distance between those and divided by total number of points. Okay, that's how it is. Or you can just say that if you subtract the one corner from another, you will get similar answer. Okay, if you pick 2 points randomly in uh, like a million dimension hypercube, the distance is going to be roughly this much, which is really huge. Okay. Okay, so is there a better way to compute? I'm just thinking, how can I compute the, if you pick 2 points randomly and okay, so the chance of, all right, let me just get back to this one. Can I do it using mathematically or empirically? We can do that. All right. Now, moving ahead, there are a couple of more ideas that I want to discuss, and we will go into more dimensions and we'll try to understand it. So, some more important observations about large dimensional data sets is that higher dimensions are at risk of being very sparse. If you have like truly like a million dimensions, it's there are there are there are many values in many values possible. So most training data sets are likely to be far away from each other. Okay, so here you can see that these are three-dimensional space and these instances are spread over all the data points like this, right? And so but if you think about it, if you have like let's say 10 let's say integers from 0 to 10, okay, and you have three dimensions, so you need 10 into 10 into 10, 100 instances to just fit in to this smaller space. Okay, if you have like a million dimension in case of an image, if you have 1,000 by 1,000 resolution image, you will have a million dimensions, and to fit a million dimensions, how many points do you need? Let's say each dimension you have 20 values, so you will need 20 to the power a million. That's actually huge set of values. Therefore, most of the high dimensional spaces are, are basically very sparse. Most of the high dimensional spaces are very sparse because even for like say 100 say 100 dimensions, the values that you require, even if you are varying from 0 to 100, the values you will require is 100 to 100. Okay, 100 to the power 100. That's a huge value. Even in the 100 dimensions, the number of instances that you would require is actually huge. So therefore, most of the instances in a higher dimension spaces are very sparse. Okay, so what the point we are trying to make is that most of the data set that you will get, if they have just too many dimensions, they are likely to be very sparse. It's just that they are so they are likely to be very sparse, and that means that the dimensions that we have chosen are kind of useless. We will need to come up with new set of dimensions, in which new set of smaller dimensions, in which there is they can this data set can pack very well. So the point that we are trying to make is, in most of the data sets that you will see, if the dimensions are higher, there's always a chance of reducing the dimensions without losing too much of information. Okay, without losing too much of information. Okay, that's a very important point. Most of the data sets that you see, whether images, whether any data set in which there are more dimensions than we thought, okay, or there are more dimensions, they're like 10 dimensions. Even 10 dimensions is huge. If the values is varying from 0 to 100, even in 10 dimensions, we have 100 to the power 10 in order to get the densely packed. Okay, so even if it's 50%, it'll be 50 to the power 100. Those are too many instances. 50 to the power 10 or 20, whatever. So the important point is that higher dimensional spaces generally are very sparse, and therefore there is always a scope of reducing the dimensions. There's always a scope of reducing the dimensions. So new data set will also be likely to be far away from any training instance, making predictions much less reliable. All right, this is another very important aspect. If the data set is very sparse, right? So, and when the data set is very sparse, like in every dimension, there are like 3 points, then the new prediction that we'll get is basically one another instance along with these three, and therefore the predictions are going to be less reliable because the prediction is based on these 3 data points, right? Or one data point. And therefore, predictions, if you have just too many dimensions, predictions will be less reliable because in each dimensions there will be only very few data points, and doing the predictions on very few data points is very unreliable. Okay, hence more dimensional the training set is, the greater is the risk of overfitting. More dimension, if you have, let's say, one data set, one point, and you're trying to draw, the chances are you will end up overfitting. Okay, let's say all right. So when you have more dimensional data, there is a huge risk of overfitting. So it's important to bring down the dimensions in the data, not only because you could not fit the data in the memory, but you but because not only because the data is not fitting into the memory and your algorithm is failing, right? But also because since the data is too sparse in these dimensions, therefore the predictions are going to be unreliable. That's a very important point. So how to reduce the curse of dimensionality? One is increase the training size, okay, to reach the sufficient density in each dimension of the training instances. But that's never a solution, to be honest. That's never a solution. So increasing the size of training set looks very lucrative, and we can say, okay, since we don't have enough images, we have just too many dimensions, therefore let's come up with more set of images in order to have data in every dimension. Okay, so this is a common thing, that let's increase the size of the training set to reach the sufficient density, but that's hardly something that can solve the problem, because number of instances, say for example, number of instances required to reach a given density grows exponentially with the number of dimensions, right? Total number of instances that are required grow exponentially, right? So if, let's say, we want 10 numbers in every dimension, correct? In those cases, if you have 3 dimensions, you will need 10 cube. If you have 4 dimensions, you will need 10 to the power 4, these many instances, and so on. So on every increase in the dimension, the growth of need in the instances is exponential. So how to reduce the curse of dimensionality? Like, for a data set with 100 features, we'll need more training data sets than atoms in observable universe, right? This is uh, good. All right, yes, we can stop here. Thank you, Tanmay, for reminding. So we'll continue our curse of dimensionality in the next session. This is a very important chapter. Do not miss it. We are going to learn quite a few things. We are going to learn something really important. We're going to learn PCA. We're going to learn what it means, why variance, and how we can think of data with huge dimensions as small dimensions. We'll continue from here in the next session. Great set of questions, great set of discussion. I look forward to see you in the next session. Have a great day. All right, so yes, I agree that Taylor series and all of that was a little too mathematical, but this was something kind of required. All right. The PPT and the recordings will be available most likely tomorrow. Do you want it earlier? All right. So great to have all of you in the session. I look forward to see you tomorrow. Have a great day. Bye-bye. All right. Feel free to let us know in case you're not able to find the find the slides or PPTs. Also join the group that Ajay had created. All right. Have a good day. Bye-bye.